Today we're going to look at the second part of 8.5. So a few more concepts, a lot less vocabulary than yesterday, but we're going to get into a couple different word problems. We're not going to focus as much on sketching unless we have a word problem. We're going to try to do things more with just numbers rather than having a sketch. So first thing we're going to look at is what it means for two vectors to be equal. All that it means for two vectors to be equal, if you have a vector with a horizontal and a vertical component, and another horizontal and another vertical component, is it just means the components are the same in each vector. What it doesn't mean is they're drawn in the same spot. Nope. The vectors don't have to have the same start point or the same end point to be the same vector. They just have to have the same components. So let's actually go like this. If I bring up, let me put a grid so I can do this kind of nice. So let's say we have the vector 2, 3. Starts here, 2 right, 3 up. If you draw another vector somewhere else on the grid that goes 2 right, 3 up, those are the same vector, even though they don't have the same start point or the same end point. They are the same vector. Questions on that idea? Okay. So, we've been writing vectors with these angle brackets, right? And we've called that, I think the book calls that an algebraic vector. Well, the most common way that we're going to see vectors written is what's called unit vector notation. This is the notation you probably want to be most familiar with on the test. I'm not saying you won't see the other ones, but you're going to see this one a lot. So it's called unit vector notation, so that might be a good place to start. What's a unit vector? Can someone remind me from yesterday?
Isn't that a vector that's just like 1 unit long?
Right, it's a vector that's 1 unit long. They're in 2D. There are 2 special unit vectors. The first special unit vector is I. And that's bold because it's a vector. And I is defined to be a unit vector that points 1 unit to the right. That's always the definition. I is a unit vector that points 1 unit right. If you want to see a picture of it, it's right there. So I is 1 unit long, and it points to the right. The other special unit vector that we use in 2D is J. So J is another special unit vector, and it points 1 unit up. So if you're picking names for vectors, you're not allowed to pick I or J. And technically when we get to 3D, you're not allowed to use K either. If you want to think of this a little bit more general rather than thinking of up, down, left, and right, you can think of I as being 1 unit long, and it points in the positive x-axis. J is 1 unit long, and it points in the direction of the positive y-axis. And if you say it that way, then it makes K very simple. It's 1 unit long, and it points in the direction of the positive z-axis. When we get into 3D, up, down, left, and right really don't have as much meaning. We really want to say x, y, and z-axis. But for today, it's just going to be 2D. And here's a picture of J. 1 unit long, and it points up.
What would happen if we had complex numbers?
With vectors?
Yeah.
I'm not really sure. I don't know if I've ever studied vectors with complex numbers.
Because wouldn't it get confusing using I as a vector instead of having complex number I?
Yeah, I'm sure there's an application for it, but I would have to see it. But yeah, you'd have to be careful with having I's. That's why they would bold it, or maybe even just use the arrow on top of it to clarify that. So essentially what we're going to do is use these i's and j's, pretend like they're building blocks. We're going to stack i's and j's together, and that's going to help us to make a vector. So let's take a look at our first example where we're going to build a vector from these pieces, these i's and j's. All right, so let's build the vector 3, 4. First thing, let me just sketch it. So it's right 3, up 4. And what we want to figure out is how many i's we need to stack together and how many j's we need to stack together to get us from the origin, or from the initial point to the terminal point. Let's start with the i's. How many of those i's would I need to stack together to start to get me to the terminal point?
3.
Yeah, I would need to stack 3 of them together. So there's 1, there's 2, there's 3. So if you stack 3 of the i's together, it's starting to get you to where you want to be. And what would you call this vector?
3i.
It's the vector 3i. So that's the first part of it, 3i. And now, how many j's would you have to stack together?
4.
4. 1, 2, 3, 4. And what would you call that vector in purple? 4j. And if you took 3 of the i's and you added 4 of the j's onto the end of it, and now think of it just like we did yesterday. Connect where you start to where you stop, you'd get exactly that vector in red. So that's what we call unit vector notation. For this one, it's 3i plus 4j. Now, if you had to go to a spot like this, that's fine. You can do a half I if you need it, just like anything else. But that only lets us go right and up. What if we had to go left or down?
Would you just make it negative?
Yeah, we could use negative i's and negative j's because that would flip the direction. So by using positive and negative I, you can go left and right. By using positive and negative j, you can go up and down. So that means you can get anywhere you want to get in 2D using i's and j's. Not 3D, okay, but 2D you can go anywhere you need to. Yeah.
So, for the vector, isn't it just writing the vector with an I and j, like left plus, like, would it always be, if it, let's say it was 6, 7, would it be just 6i plus 7j? Is it always like that? Okay.
Yeah, you take away the brackets, you take the comma out, you put the symbol in the middle, and yeah. We'll practice doing each notation a little bit, but yeah, it's a pretty, this number is always this number, and that number is always that number. The only time you can run into a little bit of a problem is if you write something like I minus j. You have to understand that there's 2 numbers there, but they're invisible. So if you were going to rewrite that, that's 1 comma negative 1, even though you don't have a 1 and a negative 1 there. Okay. All right, so let's look at some different formulas for vectors, and these formulas are going to allow us to do some of the things we did yesterday: add, subtract, scale, but we're not going to have to do any sketching. Like the first, I think it was like problem 6 through 10 in homework or something like that. You're not going to have to do it like that. We're going to do it with just numbers. In the formulas I'm going to show you, v and w are going to be vectors, and alpha is going to represent a scalar. And remember again, what can a scalar do to a vector? Really 3 basic things. Yeah, so it's when you multiply, and it can cause the vector to
Become bigger or smaller.
become bigger, smaller,
Flip.
and flip.
It's
All right.
the same.
Yeah, and if it was a 1, yeah, it would stay the same. All right, so here are your 2 vectors. Okay, I've written them in the notation we used yesterday. I'm not using unit vector notation right now. x1 and y1 are the horizontal and vertical components of v. x2 and y2 are the horizontal and vertical components of w. If you want to add two vectors together. We don't have to draw it and then position the other vector and then draw the diagonal. All we have to do is add the horizontal components together, add the vertical components together, and that will give you your new vector. If you want to subtract, same idea. Subtraction was a little bit more annoying yesterday because instead of subtracting, we had to think of it as adding the opposite. So we had to take the second vector, we had to flip it around, and then we could add it onto the end of the first one. Well, now we're kind of getting away from that. We're just going to subtract the horizontal components, subtract the vertical components, and that's the answer for the new vector. If we wanted to scale a vector yesterday, like let's say you called this v, and you wanted to find 5v. Well, you'd have to take 5 of them, stack them all up like that, and then that would be, once you draw in your vector, that would be your final answer. Well, all we really have to do to scale a vector is scale each component of the vector separate. So you multiply the horizontal component by what you're scaling by, and multiply the vertical component by what you're scaling by. So it's kind of like doing a distributive property to each component. And the last formula, which we didn't talk about yesterday, was how to find the, well, actually you tell me. What does the symbol mean? Yeah. How to find the magnitude. And the magnitude basically is the what? Using a simple word.
Force, speed, distance, length.
The length. Yeah. So the magnitude is how long a vector is. What could it represent in a word problem? It could represent speed or force. It does not represent direction. Right. So let's say, you know what, let me use a grid again. Say we have, let's take the vector 3, 4. So let's, I know it's probably a little hard to see the squares. Start here. I'm going to go 3 right, 4 up. How could you find the length of that vector? Or how would you find its
Pythagorean
magnitude?
theorem.
Yeah, we just do Pythagorean theorem.
I know.
So if you have the vector 3, 4, this is x1, this is y1. So the formula for the magnitude would be the square root of the horizontal component, square it. Take the vertical, square it. Add them up and take the square root. And I think that's the formula I put right there. So the magnitude isn't really a new concept. It's really just finding the hypotenuse of a right triangle. All right. When you do the first one, v plus w, what type of answer do you get when you're done, after you add two vectors together?
Vector.
You get a vector. Okay. It could be a positive component or a negative component, but the point is you get a new vector. How about when you subtract vectors? You get a new vector. When you scale a vector? New vector. When you find the magnitude of a vector?
Same vector. Maybe
Well, we're just finding a vector,
equal.
aren't we?
Yeah.
Yeah, we're just,
What is this?
You get a positive vector.
You don't have to think about it in terms of a word problem. Just kind of be as general as you can.
New distance, new vector.
It's not a vector.
It's the line.
It's a length. It's just a number. Yes. So, yeah, it's just a number. Okay, that's important to understand. This last calculation doesn't give you a vector. It gives you just a number, 12. Okay, something like that. All right, so let's try this. Here's our two vectors. 2i plus 3j and 3i minus 4j. Let's add them up. And let's do the answer first in unit vector, and then let's do it again as an algebraic vector. All right. So, what would be the horizontal component if you add these vectors up? And a component is just a number. You don't have to say anything else, because I said horizontal. Yep. Yeah, 5. So yeah, the horizontal component is just 5. Put the I there so we know it's horizontal. And what about the vertical?
-1.
Negative.
1.
I need more.
J.
J.
Wow.
You
Yeah.
could put negative 1j, or you could put negative j. But yes, the horizontal component is a vertical is negative 1. Any question about leaving the 1 off there? That's fine. How would you write it if you were going to do it this way?
5
-1.
5 negative 1. Yep. Questions on that? All right. So let's subtract them. V minus W. Okay. What's the horizontal if I subtract?
-1.
Negative 1.
I.
Negative I.
You can put negative 1i. I would just put negative I, but negative 1i is okay. And what about the vertical?
7j.
Right. 3 minus negative 4. 7j. And if you write it, the notation we learned yesterday,
-1 7.
negative 1, 7. Same thing. Any question on that one? All right. Both of those involve two vectors, adding and subtracting, or what you call a binary operation, because you need two of them to do the operation. Scaling is not. You only need one vector to scale, so this one we're not using W. What would 3v be?
6
Plus 18. No, 9.
9.
So 6i, yeah,
Plus 9.
and plus 9j. So these formulas are taking the place of everything that we had to do yesterday with the sketch. All right, we're still going to do some sketching when we do the word problem, but not the simple things like this. And this one, the magnitude of V. What's the first thing I should write down? I usually put this so I don't forget to do it after.
Square root.
Yeah, let's just put the square root. And it's going to be the square root of 2 squared plus 3 squared. So that's the square root of 13.
Oh.
Now, the same rules apply to square roots. If you end up with like square root of 20, you need to reduce it to like 2 square roots of 5. Any question on that kind of thing? All right. So, remember what we said about unit vectors, okay? We've said this several times. A unit vector is just a vector that has a length of 1. What I want to do is come up with a formula that can turn any vector into a unit vector. So the formula is basically going to scale it. If it's too long, it'll make it shorter, so it's 1 unit. If it's too short, it'll make it longer. So to figure out what you need to scale it by, let's just look at some examples, and I think you'll see a pattern. So here's an example where, say, the black vector is too long, and we want to scale it to make it 1 unit long. Notice the direction it points is the same. We just need to make it longer or shorter to force it to be 1 unit. So let's say we had a length. And then in this column, what to scale by to make the length 1. So let's say we had a length of, I don't know, 5. What would you scale it by to make it 1? Yep. 1/5. Okay. What if the length was 10?
110.
110. What if the length was 130? 3. So what if the length was x?
1 over x.
1 over x. So if you have a vector and you want to force it to be 1 unit long, you scale it by 1 over its length. If it was already 1, then you'd be scaling it by 1. There'd be no change. Now, scaling it by 1 over its length is really the same as dividing it by its length. That's the same thing. Yep.
Would that be the same as a reciprocal? Or
Yeah. Yep. So, to find a unit vector, if you're given a vector, you're basically going to do this. Let's let x equal the length. Or actually, you know what? Let's do it like this. I got an even better way to write it. Let's call this vector v. If you want to force that vector to be 1 unit long, you're going to go like this. You're going to multiply it by a scalar. What scalar are you going to multiply it by? 1 over its length. 1 over the magnitude. Now, another way you can think about that is instead of multiplying by 1 over something, you could just think of it as this. That's the same thing. If you take a vector and you divide it by its length, it's like distributing this fraction out. Well, if you distribute that out, you're going to end up with a magnitude of v in the bottom of the x component, and you're going to end up dividing by a magnitude of v in the y component. So you're going to end up dividing the x and the y by the magnitude of v. All right, so there's a couple different ways you can think about it. But that's generally how I think about it. Take a vector and divide by its magnitude. What does that really mean? Distribute 1 over the magnitude to each component. Just like this. That's the same thing. Right, so this kind of problem generally has 2 steps. Step 1 is to find the magnitude, and then step 2 is to divide everything by it. And that will force your vector to be 1 unit long, but it won't change the direction. Question on that idea? Yeah.
if you had a fraction for, I guess, the magnitude, how would you write that?
So you'd still multiply it or scale it by 1 over its length. So basically what happens every time is it's always the reciprocal. Even if it was like 2/3 was the length, you would scale it by 3 over 2.
Okay.
Because if you multiply 2/3 by 3 over 2, you get a length of 1.
Okay.
All right, so let's try this one. So it says find a unit vector for this vector. So in other words, give me a vector that points in the same direction, but is only 1 unit long. If this vector is already 1 unit long, then we're done. There's nothing to do. What's the magnitude of v in this case? 5. 3 squared is 9. Negative 4 squared is 16. 9 plus 16 is 25, and then take the square root. So what do we have to scale our vector by? 1/5, which essentially means if you're going to multiply 1/5 to each of these numbers, you're just dividing each one of them by 5. That's all you're doing. So the unit vector, we always use u for unit vector. So probably another letter you probably don't want to use for vectors. So the unit vector would be, you tell me, what's the horizontal? So if I write it this way, yeah, I'm just going to go 3/5 and negative 4/5. If you want to write it the other way that Mabel said, that's fine too. same way of writing, two different ways of writing the same answer. Okay, questions on that one? All right, so the last two things we're going to look at, this focuses on the word problems. This one is a lot easier than the second one. Okay, so this is a velocity vector. So what we're going to do is come up with a formula that describes the velocity of an object. And it's going to be described in terms of two things: how fast the object is going and the direction it's going. How are we going to do direction? We're going to do direction as an angle, just like an airplane does it. We're going to use an angle. Now, if you think about throwing an object, or think about this board, right? Think about something traveling on the surface of this board. Like this object. Pretend like there was an object here and it was, shot out straight like that. What direction is the object traveling in?
B.
So think about what are the directions you can travel on this board. So you could think of it as a compass, like you could go north and south, that's one way. And what other way?
We can do the eagles.
What?
If an eagle and a child look at a 45-degree angle.
So wait, what are the two, I just want to know what are the two directions we can kind of go on the
I
board.
and J.
Like,
Left and right.
up, down, left, right.
Okay, so we're not using north and south anymore. Got it.
Oh, west, east.
Up and down. No, he said up, down, left, right. So we're going with that. Don't switch back. Up, down, left, right. So this particular object is traveling in two of those directions, the up and the right. Right? Those are the two ways that it's going. So what we need to do is break that down into its components and figure out what is the up component and what is the right component. So the way we're going to do it, we're going to make a line, put it right at the end. So what we've done now is we basically made a triangle. Here's the right component, and then here is the up. And if you combine the red one with the blue one, you would get the one in black. Question on that? Okay. So there is an angle here, and we want to figure out a formula that's going to involve that angle. Now let's call this side x, and let's call that side y. Let's start with x, right? Because what we have right now is basically something like this. X represents the horizontal component, and y represents the vertical. How could I come up with a formula that involves x, theta, and vector v? What?
Cosine.
Yeah. So we could use cosine. Start with that. And what always goes in these two spots? Sometimes it's variables. In this case it will be, but yeah, lengths. Okay, keep that in mind. Lengths go in these spots. Lengths. What's the formula for cosine?
X over, adjacent over hypotenuse.
Adjacent over hypotenuse. So that's the length of that side. How would you represent the length of the hypotenuse?
Would that be the square magnitude?
The magnitude of, I'm just going to do it in bold, v. You don't want to put v in the bottom because that's not the length. It's the magnitude of v, which is the length. Right? And we said we're going to let x represent the length. So that's how we did it. Now we're just going to solve for x. Yep.
Can we just put x plus y in the bottom?
Put x. Well, when you write a velocity vector, you're not allowed to use the horizontals and the verticals. You have to use an angle and the length of v, which represents the speed. Those would be the things that you would normally know when you do a velocity problem. What angle did you throw the object at? So I threw the object at a 20-degree angle, and the speed I threw the object at would be the length of that vector in blank. Those are the two things you would know. We can figure out the horizontal and vertical components of how you threw it, but those would never be given to you. All right, so what's our formula for x?
Cosine beta divided by multiplied by magnitude of v.
All right, so here's the formula for x. And in general, this might help when we do the next word problem. Anything involving a horizontal usually uses cosine function.
They will try and knock you out.
So that we're going to fill in there. And what would be my formula for y? Anyone think they could just tell me without going through the whole thing?
Sine.
Okay, we a little bit more.
Magnitude of v sine theta.
Yep, it would be the magnitude of v sine theta. And now you can fill that in for y. So now we can write our velocity vector. Let's do it two different ways. We can do it as an algebraic vector, or we can do it with I and j. I and j is more common, but I'll start this way. So the formula for a velocity vector. You can do magnitude of v cosine theta, comma, magnitude of v sine theta. Right, so that's one way. Or, if you want to think of it in terms of the I and j, that's the horizontal. So the magnitude of v cosine theta, that number would go in front of I, plus magnitude of v sine theta would go in front of A.
Do we have a trig identity for that?
When we have things that are squared, like sine squared plus cosine squared,
So that's how to find the velocity.
yeah, and they're going to give you these two things in the problem. This is an initial speed, because remember, the length of the vector represents speed when you're doing velocity. So that's the initial speed that the object is thrown at, and this is the angle the object is thrown at. And if you plug those two things in, you're basically solving for two sides in a triangle. When you write it in that format, it tells you the vector for the object, which describes two things at the same time: its speed and its direction. Question?
When you're representing velocity, isn't it usually like feet per second or meters per second? So wouldn't the x-axis be time, and then is it v, like the magnitude of v would just be distance traveled at a certain time?
If we were graphing a graph of velocity, yeah, you could have distance and time as your labels. We're not going to be graphing it, but yes, those are the two labels you would use with velocity: distance and time. Yep. All right. So this is basically just describing what I just told you. So we already did this. All right. So suppose we throw an object 50 miles an hour at a 30-degree angle. Find the velocity vector, and then explain what each component means when we find it. Let's do it with I and j. How would I set up my component for I? What would I need to know the formula, and I need you to plug those numbers in.
Maybe 50.
50 is my speed, so that's the magnitude of the vector.
And then
Cosine
cosine.
30
Cosine 30. I, yep,
plus 50 sine 30.
there's my speed. With the verticals, or anytime you're doing something vertical, it usually involves the sine function. And the angle is J. Alright, so now, let's type that in and see what we get. Make sure you're in degrees. 50 cosine 30 gives me 43.3 I. And 50 sine 30 gives me 25J. So that's the velocity vector if you write it out in I and J notation. You could also write 43.3, comma, 25 and use the angle brackets. All right, so we did that. Now explain each component. Well, what is that 43.3? Yeah?
The distance of, no, the distance of travel.
So this doesn't represent distance. This represents velocity.
Speed. So it's the speed.
What,
No,
what
it's
about
not
the speed?
It's the speed of travel.
Is it the right or second?
Horizontal speed.
It's the horizontal speed, yes. So what that would basically mean is if you threw an object at 50 miles an hour at an angle of 30 degrees, and somebody was like standing in front of you, with a radar gun, and they clocked how fast it was coming at them, it's coming at them at 43.3 miles per hour. Why not 50? Because you didn't throw it perfectly straight. If the ball was going exactly straight and it wasn't going up, then it would be coming at you at 50 miles an hour. So some of the energy is used in just sending the ball up, and that's the speed in the vertical direction. So that would be like the speed if you were above this situation and you aimed a radar gun down at the ball. It's coming up at 25 miles per hour. And that would be its maximum speed, because the problem with the vertical speed is it's constantly changing. The ball is going to go up, and then it's going to hit a vertical speed of 0, and then it's going to start coming back down again. So the vertical speed would be the second that the ball leaves your hand, because that's when it's going the fastest. The horizontal speed never changes. It's always 43.3 miles per hour. So another thing you could do is if you had some way to project objects at very precise speeds, you could aim like something that could launch an object at exactly 43.3 miles per hour at an angle of, it would be 50 miles an hour at an angle of 30. And you could set up another ball launcher thing that could project something at 43.3 miles per hour exactly horizontal. And the two objects would basically reach their target at exactly the same point. They'd travel together. One of them would be going perfectly flat, and the other one would be going up and then back down. Okay. Any question on that? So that's velocity vector. Okay, so the last one. Static equilibrium. Well, you look at that word, let's look at the second word. What is equilibrium? Balanced. Everything is balanced. Okay? Equilibrium essentially means that the object is not moving. Right? If it's falling, that's not equilibrium. If it's just resting somewhere, like a desk or something on the desk, it's balanced. So an object is in static equilibrium if all the forces acting on it are 0. So if you look at the pen right there, that's in static equilibrium. Gravity's pulling down on it, but there's also a magnet that's pulling up on it and holding it where it is. When the sum of the forces acting on an object is not 0, then you get acceleration and something starts to move. Static equilibrium means everything is balanced. Now, I want to think two-dimensionally about things being balanced. So think about this board again. If forces are balanced, there's a couple different directions we have to look at. What are the different directions that we can travel on the board again?
I want to have line back.
North,
Yeah.
south,
Up and
west,
down.
east.
No, left and down. Up, down,
Left, right.
left, right. So if an object is on this board and it's not moving, that means that the forces up and down are balanced and the forces left and right are balanced. Those are the two different directions. We don't have to worry about forces in or out. Okay, that would be more of a 3D. So essentially what we're going to do is look at a problem like this. We've got 1,200 pounds being suspended from two cables, and I want to find the tension in each cable. Now, first thing to understand is you can have more tension in the cable than the object weighs. Because think about, like if you had a tug of war, and maybe you had a big rope, thick rope, and maybe the rope weighed like 50 pounds. But if you get 40 people on one side and 40 people on the other side pulling on that rope, there could be a lot more tension in that rope than just 40 pounds of tension. And the rope might not even be moving, but there could be a ton of tension, and you could tell because if you cut the rope all of a sudden, everybody would fall because there's a lot of tension. All right? The only way that the amount of tension in the cables is exactly equal to the weight that it's holding is if they're vertical. Then yes, the tension in the cables would be distributed equally by the weight. So like if you look at the light on the ceiling, assuming that the light is uniform and the cables were equally spaced, but that last one's not quite. So if they were all equally spaced and that light weighed 40 pounds, then that 40 pounds would be divided by each cable that's holding it because they're perpendicular. These cables are not pulling against each other. Now, if you look at like the strings holding up the curtain in the front, those are at an angle. So they are actually pulling against each other. Because if you cut one of the cables, like if you had something like this is actually simpler because it's only one and one. If you cut one of these cables, what would happen to this weight?
Swing.
Which way?
It depends on which one
The
you cut.
opposite.
Well, if you cut this one,
Then it would go right.
then it would swing to the right. So this cable over here is not only holding it up, it's also holding it from swinging to the right. So this cable is pulling on it in two directions. It's pulling up and it's pulling left. This cable is pulling up, but it's also pulling right. You don't get that horizontal pull if the supports are vertical, but in this case they're not. And they're at different angles to the ceiling. So there's going to be a different amount of tension in each cable. All right, so let's see if we can start to set this up. This object is not moving, so we know it's in static equilibrium. That means that the force pulling up on it is equal to what other force? The force pulling down. What we're doing right now is just trying to set up kind of what I call like a conceptual equation. It's not really any numbers or letters or variables yet. It's basically an equation with ideas in it. Force up equals force down. And what other forces are equal?
Force left equals force right.
The force left is equal to the force right. Any question on that idea? All right. Now, what we want to do is start to break down the forces up and down in this diagram and give them names. So what I need to do is draw some horizontals and verticals, which is going to allow me to break apart these vectors. Use different colors. So there's one vector pointing up and to the left. Here's another one pointing up and to the right. I want to find the components of each of those vectors. And the way I'm going to do it, I'm going to need a couple verticals, and I'm going to need a horizontal. So by putting those in, what did I basically just create? Triangles. Triangles all over the place. So let's start with the one on the left. This is the vector pulling left, and then this is a vector pulling up. If you put the blue and the green together, you would get the one that's in black. And let's call that one in black, let's give it a label. Let's call it T1, because that'll represent the tension in cable 1. And let's call this one T2. And let's decompose that vector into its components, the horizontal and the vertical. That vector in blue, I'll put a space so you can see it. That one represents the horizontal force for T2, and this represents the vertical force for T2. Questions on that? Now, we want to name those two green and two blue arrows. Not finding any numbers yet, just want to name them. What letters do you think we should use for the horizontals?
H1 and H2.
Okay, we could use H1 and H2. Yep. Just don't want anyone to confuse that with hypotenuse. Maybe probably wouldn't do that. But what other letters are commonly used for horizontal? Yeah?
X.
Yeah. So we could call this one X1. I would keep all the ones together. So this is the horizontal force for cable 1. And what about this green one?
Y1.
Call that Y1. And what about this blue one over here? So you can call this one X2. And the green one? Y2. Now, we're going to start to transfer from kind of this conceptual idea to more about our diagram. Still not going to have any numbers. Well, we might get one number. But we haven't really done anything with angles or that stuff yet. Okay, we're getting there. What are the up forces in this picture? Y1 and Y2. And are they working together to hold the object up, or are they fighting each other?
Yeah. Or fighting.
Together.
They're working together. It's not like one of them is pulling up and the other one's pulling down. They're both pulling up. So they're working together to hold the object up. So how would you represent force up? Y1 plus Y2 equals. Now the force down, we know that. What is the force down? 1200. That's the weight. All right, so there's our first equation. That's the only number we're going to have for now. What's the force that's pulling left in this diagram? X1. And what's the force that's pulling right? X2. So now we've gone to this kind of just general idea to something a little bit more specific that's actually using labels in our picture. Now we have to figure out all 4 of those. The way we figure them out is exactly the way we did it for a velocity vector. Let's see if we can label some things in these triangles. Well, we know these are 90s. Yeah, and we could label, really, we could figure out either one of these angles. It doesn't matter, let's do, let's just put this one as a 30. And we could put this one as 45. It doesn't matter which angle you figure out. I just did that one. Any questions on how I figured those out? Okay. Now, let's come up with a formula for x1. So I want to use x1, 30 degrees, and the tension in cable 1. So the idea now is you have to get rid of all these x's and y's. All you can have in your final equations are t1s and t2s. No x's, no y's. What trig function would you use that relates x1 and t1?
Cosine.
Cosine. So the cosine of 30 would equal, and what's the fraction? Yeah.
X1 over T1.
X1 over T1. And now solve it for X1. What is it?
T1 cosine.
T1 cosine 30. Right, now do that 3 more times. Find a formula for x2, y1, and y2. Let's do the other x while we're here. Just do that one. 45, x2, t2. What trig function would you use there? Cosine. And the cosine of 45 would equal
X2 over T2.
x2 over t2. And what would x2 equal?
T2 cosine.
T2 cosine 45. Second. Any question on those two? I'll do it for the y's. All right, so focus on y1, this angle, and t1. What trig function would we use for the red circles? Sine. All right, so sine of 30 degrees equals, and what would go on the other side?
y1 over t1.
Y1 over t1. And solve for y1. T1 sine 30. And the other one, I'll just do it real quick. Or does anyone think they can just tell me what it is?
T2
T2
sine 30.
T2 sine 45. Yeah. If it's a horizontal, it's always cosine. If it's a vertical, it's always sine. And then you just put the hypotenuse of the cable. So you can just follow that pattern. All right, so now we've got 1, 2, 3, 4 boxes. Substitute in 1, 2, 3, 4 things. And that's going to give us our final equations we need to solve. And then from there, it's a system. Okay? But that's, at this point, we've done all the trig. This is kind of the physics part right here, the black. The trig part is figuring out all 4 of these substitutions. And then the algebra part is solving the equations. All right, so let's start with y1. What's y1? T1 sine 30 plus y2.
T2 sine 45.
T2 sine 45. What else do I have there? That equals 1200. So now look, you only have 2 variables in that equation, and you're going to have the same 2 variables in the bottom equation, just like a system. x1, t1 cosine 30. Yeah, what's the other one? x2. Okay. So here are 2 equations to solve.
Wait, what one would be sine?
Yep, top ones are sine, bottom ones are cosine.
You could plug in T2 cosine 45 to the T1 sine 30.
Yeah, so we've got to get T1, you've got to solve for T1 or T2. Which equation is it easier to get the T1 and T2 alone?
The first one.
You think it's easier to solve for T1 here or here?
Second one. I don't know.
I think the second one, because I only see one thing you'd have to do to get T1 or T2 by itself. To get the T1 or T2 by itself here, I see 2 things you'd have to do in the top one.
Could we just do like this substitution?
Yep, so what do you want to substitute for?
Well, you can do the top one and okay, no.
So we can do the top one. Let's say we want to substitute for T1. Now solve the bottom one for T1.
Oh, you have to get T1 all right.
You have to get T1 by itself.
Never mind, maybe the bottom's easier.
What would T1 equal if you get it by itself?
T2 cosine 45 over cosine 30.
So T2 cosine 45 over cosine 30. And now, substitute that in. We're getting to a point we need a calculator pretty soon. Substitute that in for T1. So we solve the bottom equation for T1, and we're substituting it into the top. All right, so let's write out the top equation, and then we'll be able to get T2, and then T1's easy. So T2 cosine 45. If somebody has a calculator, that's going to help in a second. So what is it? T2 cosine 45 over cosine 30. Times sine 30. Anyone have the rest of it? So I don't have to. Plus T2 sine 45. And what's that equal to? 1200. Now, how many different variables are in that equation? One. Easy. Just one variable. I need to multiply all this out. I need the cosine of 45 divided by the cosine of 30 times the sine of 30.
Couldn't you multiply both sides of the equation by cosine 30?
You could, but you have to do that by terms. So then you'd have to multiply it here and here. Not sure it would really save a ton of work. But anybody have what this comes out to? And you type it in?
I got 0.408.
0.408. All right. I know the sine of 45. That's 0.707. Right. Now, these are like terms, so I need someone to add those up. What's 0.408 and 0.707? Add it together.
1.115.
1.115. And last thing I need is to divide 1200 by 1.115.
1067.23.
106.
I got 1076.
Or sorry, 1076. Yeah.
1076.23. Okay, so that's the tension in cable 2. And now, to find the tension in cable 1, just do it right here. Take 1076.23, multiply that by cosine 45, and divide by cosine 30.
I got 878.74.
878.74. Okay. So that should be the tension in each cable. Definitely more than the total weight of 1200, but that's because the cables are pulling against each other. So once you do enough of these, you can almost jump to this step each time. Once you understand that it's always going to be x1 equals x2 and y1 plus y2 equals your total weight. But that's kind of how you go through it from scratch, from idea all the way to your solution. All right. So homework, again, it's section 5.4 in the other book. But I am going to take off one of the questions.
What's odd?
You don't have to do 69. The 25 to 47, that's the odd.
Oh, okay.
And then 55, 57, 64. Actually, no, we could skip 64 too. All right, so we'll take a look at that.